Okay, so I'll first say a few words about the midterm, which will be on next Monday. So I would like to say that we will do it remotely, as we said. So on next Monday, we will make the exam available for you at our class time, at the beginning time, start time of our class on CCLE. So at that time, everyone should be able to download exam, and also you are going to submit your answer in an Excel file we'll provide you. I think at least that's my plan for now. So you're going to upload the exam, the answer as the Excel in the Excel sheet we'll provide you to CCLE before the cutoff time, which will be the end of the class time. So basically we'll just use the 115 minutes, which is 1 hour and 15 minutes for the exam, the class time for the exam. So we'll see how it works. We'll do this remotely, and other problems will be multiple choices. And please be assured that we are not going to ask you to do a lot of calculations. So basically the problems will be conceptual. If you understand it, then calculation shouldn't be the burden. Okay, so we'll try to focus on the concepts. And also, I want to say that regarding the, I want to say that because we're going to focus on the concept, we will use notations instead of numbers for many problems. So I would say that for notations, I just saw a question on CCLE, which is about the notation that T sub 0. I think for that one, which is in problem 7 of your homework 4. So I think that's a very good example to show that the interpretation of a notation is context specific. So even though we use the T sub n to denote a T distribution with n degrees of freedom in our class, right? But in that context, the T0 actually means a constant, which you need to find instead of like a T distribution. Because, you know, when we have a probability statement, like a random variable greater than something, then that something couldn't be a distribution. It must be like a constant or like a random variable itself, depending on the context. So I think that's a good example to show that we shouldn't remember or memorize the notation rigidly. Instead, we need to interpret meaning in the context. And this will be universal for all the future statistical notations you will see. So for example, sometimes we refer to a dimension by P, sometimes we refer to by the dimension by D. So these are common notations, but you need to see what the context is. So I'll try to make sure that in your exam questions and future homework that the context is very clear. So there's no confusion for that. All right, so and also for the exam, please be sure that when at next time we went to exam, so we will require everybody to turn your camera on. That's our policy. So make sure that you are in the condition that you can turn on your camera. If there's some technical issue with that, please let me know by email. So you can email me privately so we can figure that out. And also if you need additional time for the submission, we will accommodate that, but you need to have the approval from the CAE beforehand. In that case, so we can allow you to have additional time, and then you are going to submit the exam answers to me by email, because the CCLE time is for the majority of people who will have that 115 minutes. Okay, so that's my plan. And is the cheat sheet? Yeah, of course. I would say, yeah, this is still, yeah, the same policy as in the syllabus, even though we're doing this remotely. Yeah. Okay. Okay, so this is my first time doing this, teaching this class and having this exam remotely. So hopefully we can work it out. Okay, so that's all I want to say. And please be assured that I think if you feel comfortable with the homework problems, then the exam shouldn't be a problem, because we give you less time, and also this is like you're under more pressure, right, to solve the problem in a limited amount of time. So we'll make sure that we cover everything in the homework and lectures, and we focus on the concepts instead of the complicated calculations. Okay, so now let me start sharing. Oh, and also regarding what will be covered in exam, right? That's important. So I decided to cover everything up to the lectures last week. So basically what we talk about this week includes the method, the moment estimators, and what I'm going to talk about today will not be in the midterm. So basically the end point of that midterm will be the F distribution, chi-square distribution, T distribution. That's where we will stop. And once I started talking about last time on Monday, I talked about the bias, the properties of estimators, including the bias, and then we talk about the method, the moment estimators. Those will be in the final. I'm not going to cover it because I realized that this will be in the next homework and you're not going to submit it before the midterm. So, and also to make sure that everybody has enough time to prepare for the midterm, I'm not going to assign a homework today. So I think the next homework will be assigned on Monday after you finish the midterm and then due in the week. So therefore you can just prepare for the midterm. Hopefully that works. Okay, sounds good. Then let's start our lecture, even though this will not be in the midterm, but it will be in the final. So please still pay attention to what we will do today. Okay, so let me start sharing my screen. Okay, so just as a quick recap, what we did on Monday is that we talked about an estimator. You know, this is like the separation. Okay, before this, we were talking about probability, and now we're talking about statistics using the things we learned before. So we're assuming a random sample is composed of n IID random variables from a population, which is represented by distribution, like a normal distribution or a Possum distribution, and the distribution specified by some parameter theta. So like for normal distribution, you need two parameters. One is the mean, one is the variance. For a Poisson distribution, you need just one parameter, which is the lambda. So here we just use the notation theta in general. And then our interest is to infer this population parameter theta based on our random sample. So what we come up with is called an estimator. So estimator theta hat estimates theta. The hat means that it's an estimator, it's from our random sample. Let me enlarge my screen. So the estimator is constructed as a function of the random sample. So basically some operation on the sample, so you get the estimator. For example, if the population parameter is the mean, okay, then we may take the average of x1 to xn, and we denote that by xn bar. We call that sample mean. Then the sample mean is just our theta hat, if the theta is our population mean. All right, so the first property we talk about for an estimator is the bias. The bias means that if you take the expectation of estimator, which means that if you consider the randomness of your random sample, okay, and you take expectation to remove the randomness, would this expectation be equal to the parameter you want to estimate? If so, we said the bias is 0, and we call the estimator an unbiased estimator. All right, so we're saying we use the R coding to show that even though for the theta hat, a particular realization on one particular realization of the sample may be different from theta. But we expect that if we do the sampling repeatedly for infinite number of times, then all the realizations we take for theta hat, by averaging it, the average should be equal to theta. So that's what we interpret as the unbiasedness. Okay, so with this, then we said, oh, if we have this IID random sample from a distribution with mean mu and variance sigma squared, then we give you two random, I would say two unbiased estimators, one for each parameter. So the unbiased estimator for mu, population mean, is just the sample mean, xn bar. And the unbiased estimator for the population variance, sigma squared, is this one. This we call the sample variance. The key here is that we divide the sum of square differences between each random variable and the sample mean. So we take this sum square, and then we're going to divide by the number of observations, right? We are going to take an average because, you know, this population variance, let me just write here. This population mean is actually the expectation of each xi, all right? And the population variance is actually the expectation of each xi minus the population mean square. So therefore, on the sample level, we're going to replace expectation by average. This is what we did for the sample mean. For the sample variance, intuitively, we should take the average by dividing n, but we're not doing this. We're dividing by n minus 1. And the reason is that we show only with n minus 1 is this Sn squared an unbiased estimator for sigma squared. If we divide by n, then it becomes biased. So this is a thing for having n minus 1 here. And also mechanistically, we can interpret this reason of having n minus 1 here as this xn bar is not really the mu. Okay, we're using the sample mean instead of the population mean. So in other words, I would just say vaguely, we lose 1 degree of freedom by having the mean here using the data for twice. Okay, so we're constraining data to be around the sample mean, and then this becomes n minus 1 instead of n. That's a vague way to interpret why we have n minus 1 here, but the exact reason is the bias. We want to make an unbiased estimator. And after this, we introduce the bias, right? And then we talk about how to construct estimators in general, given that we have a population with some parameter theta to be estimated. So the first way we introduce for constructing estimators is called the method of moments. So the idea is very simple. We want to express our parameter as a function of population moments. And these are the definition of population moments. It's just the expectation of the random variable raised to a power. If the power is k, we call the kth population moment. And we estimate those population moments, which are themselves some parameters about the population, right? We estimate each of them by the corresponding sample moment of the same order. So by sample moment, we are not taking the expectation because we don't know the population. We are doing what? We are taking the average of our observed sample to mimic the expectation. So that's why you see this average is of xi. It's just an estimator for expectation of x. And the average of xi to the power k is an estimator for the expectation of xk. So we have that correspondence. And therefore, if you can express a parameter as a function of population moments, then the estimator is the same function applied to the corresponding sample moments. So then an example we used to demonstrate this was this one. I think the last example is a perfect demonstration of this. So here, this is the most complicated one we did last time, right? So we have a random sample from a population specified by this density function, probability density function or PDF of this form. All right, and then the parameter here is theta. We want to estimate it. And what we did is that we first compute the first population moment and we express it in terms of theta. Turns out to be of this form. So we can just rearrange the terms so that we can express the parameter theta as a function of the first moment. And then correspondingly, the method moment estimator of theta, called theta hat MOM, is the same function applied to not EX, but X and bar. Okay, so this is what we did for constructing the method of moment estimator for a parameter. And I hope this is straightforward because we are just replacing population moments by sample moments. And do we have questions about this? So this will be what we want to talk about for method of moments. And today we're going to talk about the second way of constructing estimators called the maximum likelihood estimation, which is a more popular way nowadays. And the reason is that the estimator constructed by maximum likelihood estimation, short as MLE, has better theoretical properties. Okay, so we're going to talk about the properties later, but we're going to introduce MLE today. Okay, before we talk about MLE, do we have questions about MOM? Okay, sounds good. So now let's talk about the second way of constructing estimators, which is called the maximum likelihood estimation. Short as MLE. And this is the second way of constructing estimators. Okay, so the setting is still that we have a random sample as IID, represented by IID random variables from a distribution with parameter theta, the same setting. But in this case, we are considering that the distribution has probability density function, which is known, or probability mass function, which is known, depending on whether the distribution being continuous or discrete. Okay, so let's say that if the distribution is continuous, we know it's PDF. Okay, so the PDF, we specify it by lowercase f of a function at a value that can be taken by a random variable following this distribution. For example, if the distribution is normal, then the small x can be any real value. If the distribution is exponential, then this x should be positive or non-negative. All right, and also here, one thing I want to say is that we also add the theta after the semicolon as something we make a note here. We just want to say that, yes, this PDF is specified by parameter theta. So let me give an example later. Okay, so then if it's, on the other hand, if it's discrete, we don't have a density function, but we have a probability mass function, short as PMF, probability mass function. And in this case, we are going to write it as probability mass function. We can still use the same form, but actually I can say that, maybe I'll just write this. Okay, we'll just say this is actually the probability mass function is that for a hypothetical random variable following the distribution, it is that this random variable takes this value small x, also given that the distribution is specified by theta. So let me give you some concrete examples. So for example, if we have x1 to xm IID from a normal distribution with mean theta variance 1. Okay, now theta is the normal mean and normal distribution is continuous. So in this case, this fx semicolon theta should take this form 1 over root 2 pi exponential function of negative x minus theta squared over 2. This will be the density function. And now you can see the reason we put theta here as a note is because theta is something we need in the function. So the function is fully specified. Even though the function's argument is x, which means that x is going to be changed for a different x, we get a different density, but theta is a fixed value that must be specified. All right, so for a different theta, if we change the theta, then the function value would also change for the same x. So that's why theta is the thing we need to specify here so that the density function is fully specified. All right, the second example is that if we have a discrete distribution, like IID from Possum, now I call theta the Possum parameter. Then the PMF, which is written as, I'm just using x as a notation to denote a random variable from Possum. That's it. Given theta, we'll take this form. It will be theta to the power of the small value x, small x, to the exponential to the power of negative theta divided by x factorial. So given this Possum PMF, you can see that if we change the small x to a different integer, then this probability will change accordingly, right? Given the theta being known. So in both cases, you can see that theta plays a crucial role in either the density function or the probability mass function. And you may wonder why we don't write the density function in this way. The reason is that this is a fact of a continuous distribution. For continuous distribution, this probability that big X equals small x is always 0, right? So in that case, we cannot write it, but the density is informative. Okay, so with this, then what's the idea of MLE, maximum likelihood estimation? So to define a likelihood, let's first think about this joint density. So let's say joint density, let me say, yeah, joint is either density function if it's continuous, okay? Joint density function is actually defined as this thing. We are going to actually consider what's the joint density of x1 to xn. So basically, we are going to write it as, okay, f joint density as, I'll just write this, x1 to xn, given theta. So suppose that, I'm just going to make a note here. So x1 to xn are realizations of our random variables, x1 to xn. So in other words, this is what we call our data. So the numbers we observe, the n numbers. All right, so given the n numbers, if you are interested in their joint probability density, we can write it this way. And now we're going to say that they are IID, right? x1 to xn are IID. Because of this property, we're going to factorize this joint density by the product of each random variable's density. So this can be factorized as fx1 theta multiplies fxn theta. This is what we can do given the IID. So for example, if it's the normal, all right, if it's the normal, I'm going to put the normal formula here. You can see that by multiplying them together, what I will get is simply this one, 1 over root 2 pi raised to the power m, because the same thing. And when I multiply the exponential terms for x1 to xm, I'm going to have a sum in the exponential function. So basically this will become the sum of, let's say, I from 1 to m, denominator here, I am going to have xi minus theta squared. Okay, this will be what it looks like for the Gaussian case, the normal case, I should say. Okay, this is the density case. How about the joint PMF? Or I should say the density is also PDF, okay, probability density function. So density is short for PDF. So I'm going to mark it here to avoid confusion. If they're all discrete, then the PMF is actually of this form. The probability that big X1 is equal to small x1 and up to the random variable big Xn takes value small xn at this parameter theta. Again, by the IID of x1 to xn, I can write as the probability x1 takes value small x1 given theta multiplied to the probability of big Xn equals small xn given theta. Okay, and now let's use the Possum case. If it's that example up there, then we can see that what we will have, I'll just simplify the algebra and write the result. So we're going to have x1 factorial multiplied to xn factorial in the denominator. And the numerator, I'm going to have theta raised to the power as the sum of xi. Okay, I from 1 to n, multiplying exponential to the power negative n times theta, because this exponential to the negative theta is going to be multiplied for n times. So this is the joint probability mass function we could obtain for a random sample from Possum theta. So anyway, so given this, how do we interpret this joint PDF or joint PMF? What it means is that given parameter theta, this is the chance that we are going to observe our data. Okay, so this is the, I'm going to say here, so this one, or this one. So only one of them can be existing because we have the random sample either from a continuous distribution or a discrete distribution. Okay, so either one of them means the chance of observing, I should put chance here in the quotation mark because density is not exactly the chance, but you can sort of interpret that way. The chance of observing the data given parameter theta. All right. So in this case, it says that if we fix the parameter theta, say theta equals 1, we are going to calculate the chance of observing our data. And then if we change theta to 2, we should calculate the chance separately. So in other words, for a different value of theta, the chance of observing the data will be different. Does that make sense? So different theta will give you different value for either one. So this will give us a way to think, oh, maybe I should guess the theta to be the value so that my chance of observing the data is maximized. Okay, so that's the intuition behind MLE. So let me just write it here. So MLE takes this attitude as that find the value of theta such that the chance of observing the data is maximized. Right? Intuitively, this is the most reasonable way. We want to make sure that our data is coming from a theta that makes our data more likely. Or I should say, maybe we should find the theta such that our data is just a likely observation. Okay, so based on this goal, do we have any question about this goal before I continue? This is the key to understand what MLE means. It means that find the parameter value so that we have the best chance of observing our data, the realizations, small x1 to small xn as realizations of big x1 to big xn. So capitalized notations for random variables, lowercase notations for the realizations for our actual data. Okay, so if there are no more questions, here comes to our definition of likelihood. Of likelihood, which is perhaps the most important concept in mathematical statistics. Okay, likelihood. So we define the likelihood of theta is defined as, we use this capital L to mean the likelihood function, and we define it as a function of our parameter value theta. It's defined as the joint density of our data given theta if the random variables x1 to xn are continuous, or the probability, joint probability mass function of our random variables taking the realizations given theta if x1 to xn are discrete. Okay, this is the definition. So one thing I really want to emphasize is that even though we define the likelihood function as the joint PDF or joint PMF given theta, but we cannot say the likelihood is the joint density. The reason is that here on the left-hand side, function L has theta as its argument, while on the right-hand side, function, let's say the f function here has x1 to xn as its argument. So in other words, there are two different functions by nature. Here, this f function needs n arguments, while the function L only needs one argument. That's one way to put it. And it's just that the function f itself is defined based on theta. So therefore, we just consider the same mathematical expression in another way. So let's look at this formula. Let's say, if we interpret this function as a function of x1 to xn, then we treat theta as a constant instead of an argument of the function. But when we say it's a likelihood of theta, we are treating theta to be the argument, which can change, and we consider the small x1 to small xn as fixed. So it's two different perspectives of the same function, of the same math expression. I made it wrong. Of the same math expression, we can either interpret it as the function of n arguments, x1 to xn, or alternatively, we can regard it as a function of one argument, that's theta. So likelihood takes the second perspective, while the right-hand side, the density, joint density function takes the first perspective. Does it make sense to people? That's the thing I really want to emphasize. And I've seen a lot of mistakes about this, this statement, even in some research papers published by people. Yeah. So when we say density, we regard the density of n IID random variables. When we say likelihood, we regard it as a function of parameter. Okay, so now you see that the MLE goal to find the theta value that makes the density, joint density maximized is the same as, say, find the theta that maximizes the likelihood. That's the definition. So MLE, maximum likelihood estimator of theta, of the parameter theta, is just defined. We did the notation theta hat. MLE is just defined as the maximizer. Okay, let me just write it. Maximizer of AL theta. That is the value of theta that makes the likelihood the maximum. And mathematical notation for the maximizer of a function is this thing. We said argmax L theta. So basically, and we say that, put the theta down here. So argmax means that the argument value that maximizes this function. Okay, so basically when we say argmax, we return a maximizer. So to give you a sense about what we mean by maximizer, let's take a look at here. Okay, so I'm just making up one example. So if L theta takes this form, let's say negative theta minus 1 square. All right. So I'm just making up one example, and this is a simple quadratic function. people should be able to visualize what the shape looks like, right? And in this case, we know the value of theta that maximizes function should be theta equals 1. So this will tell me that the argmax of this function L theta for all possible values of theta should be equal to 1. This is what we mean by maximizer. So if or I would say graphically, if this is what we call theta, okay, and if x-axis is theta, y-axis is the likelihood value. If we have a curve like this, okay, this is the likelihood function value, how it changes with theta. Then the maximizer is here. This is what we call theta hat MLE. It's where the likelihood function is maximized. Okay, any questions up until now about what the definition of MLE? All right, if there are no questions, then I have a question for you. So given that if we know the form of the L function, the likelihood function, what strategy do we know about finding the maximizer? This is something you should have learned from calculus. There's a chat, let me see. Yep, optimization, take the derivative. Yeah, exactly. Derivative, yep. So if we know the function is twice differentiable, then the maximizer should correspond to, let's say, here we should like this in this flat, looks flat, right? It means that here the first derivative is equal to 0, while the second derivative is negative, right? So both, if satisfied, we can call this a global maximum. Okay, yep, so thank you for the answers. So that's exactly the most common strategy of finding the maximizer. So if the likelihood just has a nice shape, so it's twice differentiable, then we can find it. All right, so let's look at the Possum case. All right, so for the Possum case, we give you the likelihood right there, up there. So let's do it. So examples, the first one is that, okay, let me scroll down. X1 to Xn RIID Poisson with parameter theta. Okay, so based on what we just said, let me see how to find theta hat MLE. Based on what we derived above, we know the likelihood of theta is, we call this L theta. It's defined as the joint probability mass function. Okay, joint probability mass function. Let me just write it here. So I'm just keeping the random variable notations and you're going to see why. Okay, so I say the random variables are x1 to xm. Let's see, they can take any values. So I'm still denoting that any value by the random variable symbol. All right, and add this theta. Okay, and then by the IID, I factorize them as the probability mass function of the first random variable, taking this random value x1 at theta multiplied by the last random variable, taking the random value big xn. Okay, so with this, and then I use the Poisson probability mass function, which I already have here. So I'm just going to copy it down. Instead that here, I'm dropping the lowercase notations because I want to say that here the observation, the realizations can be random. I can take any possible samples from the distribution. So that's why I'm keeping the randomness instead of specifying, oh, they're the lowercase ones. So this becomes the theta raised to the power capital Xi, I from 1 to m, exponential to the power n negative n times theta, and I mean here I'll use the product notation, I from 1 to n xi factorial. Okay, so that's the likelihood. And then you can see given any values of my random variable big X1 to big Xn, they can change, and this is the corresponding likelihood given my theta. Now I'm interested in knowing at what theta value am I going to maximize it. So you can see that here the maximizer, right? If we find the maximum value of theta, if we find the value of theta that maximizes this expression, we can know the maximizer should depend on x1, big X1 to big Xn. So this is consistent with our saying that the estimator is a function of our random sample, right? Because our random sample is X1 to Xn. And here the maximizer will be a function of X1 to Xn. Okay, so let's do it. So you see that if we directly take the maximizer of this, not so straightforward because we have the power function and exponential function to deal with. So therefore, a common strategy is that let's take the log of the likelihood so that we can, once we take the log, you see the power will come down and also the exponential function will be gone. Okay, so we will say that this is a key thing. So for this function, because log, you see, the log transformation is what? It's monotone increasing, right? So therefore, if we take the log of the likelihood, its maximizer is the same as the maximizer of likelihood. That's the key thing. So if we take the log likelihood, define it as, let's write as lowercase l. Lowercase l at theta is defined as the log, or maybe I say log or ln. So it's basically the log with base e, okay? Log of big L theta. So we just didn't write the e here, but it means the base e. Okay, and this log likelihood just simplifies the power terms, exponential terms. That's the reason. And the fact is that the argmax of this log likelihood function is the same as the argmax of the likelihood function, because log transformation is monotone increasing, so it doesn't change the maximizer. So therefore, since our goal is just to find a maximizer, we could just maximize the log likelihood instead of the likelihood for simplicity. Okay, now let's look at what the log likelihood is. Small l theta. Now let's do the log of this big L theta. Now it's our algebra. So with the log, you see ratio becomes log difference. And then the first term that we will get is for the numerator. This will come down, summation xi, okay? The power will come down, and this will become log theta. That's the first term. Second numerator term becomes minus n theta. Finally, numerator becomes log product xi factorial I from multiplying I from 1 to n. That's the log likelihood. Okay, do we have question for this part before we continue this log transformation? Okay, so now you can see if we regard the log likelihood, it is a function of theta. Then which two terms involve theta? This one, right? It's a function. If this is a log theta term, this is a theta term. And the third term doesn't have anything to do with theta. So therefore, it has nothing to do with our search for the maximizer. So basically, the maximizer of the maximizer theta of this function is only related to maximizing the first two terms, because they are the only two terms involving theta. Okay, now let's follow your strategy to do the differentiation, because you see log theta is differentiable, right? At least twice differentiable, and theta is also differentiable. So now let's do New piece of paper. Okay, so now let's do differentiation. So first derivative, let's do d theta of this log likelihood theta. This is the thing we want to set to 0. Okay, and let's see what it is. So this is just a multiplier, so it stays. Differentiation of log theta becomes 1 over theta. So we have right, this is what we get. And the second term differentiation becomes n. And the third term is gone because it doesn't involve theta. And we want to set this to 0. So set d theta to 0, we will obtain what? We will obtain the theta value by setting this to 0. The theta value is just equal to, I'm just writing the result, 1 over m. This is it. And this is just our definition of the notation x and bar, average. Okay, then what's left for us to verify is is this theta value leading to a second derivative of a negative second derivative, which is what we need for maximizing, right? So let's do second derivative, d squared d theta squared. Okay, now we are going to have negative, or the first term stays. Okay, and the second term becomes negative 1 over theta squared, and minus n is gone. Okay, because x1 to xn are from Possum, and Possum random variables are all non-negative. So we know this is non-negative, and also theta squared is non-negative. So together with this minus sign, this, right, is non-positive. So basically this verifies that, at least this is, and also we can say that because the theta must be positive, okay, this is just a requirement for Poisson. Theta must be positive. So therefore, I can say that this is non-negative. So with this, we can actually conclude that, okay, together with the setting first derivative to 0 and verifying that the second derivative is non-positive, so together, hence, we can say that this value, xn bar, is the maximizer of the log likelihood. That's what we conclude. So based on the definition of MLE, we write theta hat MLE is just equal to xn bar. Okay, so you see that in this Poisson case, we have the coincidence that the MLE estimator for theta is the same as the MOM estimator for theta. Recall that last time we did, because Poisson theta, here theta is just equal to the first population moment, right? Expectation of x following Poisson theta, that's theta. And then if we use the first sample moment to estimate the first population moment, that's still xn bar. So in this case, the theta hat MLE just happens to be theta hat MLM for this case. Do we have a question for this? Okay, this is our first example of showing what the MLE is. And our second example will be, this is a discrete distribution example. Our second example will be for continuous distribution. So now let's say that we have x1 to xn IID from a normal distribution with two parameters, mu and sigma squared. And we want to use the MLE to find estimators, because mu hat MLE and sigma square hat MLE. How to find those? So here, the likelihood will be about two parameters. So theta, if we still denote by theta, Here the theta will be two-dimensional, okay? So to find this, we are going to write the likelihood of, here we say theta is just two parameters. I call that mu sigma square. It's a vector. Is. And I still can write the L theta. But please note that here theta is a vector argument. Or I can spell it out. I just write L mu sigma square. So then both are scalars. And by definition, it's actually the joint density of those x1 to xn. So I'm still keeping the capitalized notation because they are you can take any values, any random values, not just a particular set of numbers. And I evaluate them at a given theta, which is given mu and sigma square. All right, and then what I can do is that I will do the IID, right? So basically, it's for each x1 given theta multiplied to the density of xn given theta. And we already have it here in my example before. So it's just but here I'm making it simpler because here the normal has variance 1, but now we don't have variance 1. So therefore, I'm going to give you the general formula. So for each one, x1, its density from this normal distribution should be 1 over root 2 pi sigma standard deviation times exponential to the negative x1 minus mu squared over 2 sigma squared. This is the density for x1. Multiplying to 1 over 2 pi sigma exponential to the negative 2 sigma squared xn minus mu squared. Okay, so n of such terms are multiplied together. So combining the terms, I'm going to have the first one appears for n times. Okay, this is what we have. And for the exponential terms, when we multiply them together, we add up the powers. So exponential to the negative, I'm adding them up, and the denominator is common. So I put the denominator here, but the numerators are added up. So I from 1 to n, xi minus mu square. You see, this is the likelihood. And because this likelihood involves power and also exponential function, again, it's easier to do the log likelihood. So the log likelihood is, I use the lowercase l theta, which can also be written by spell out this theta vector log L at mu sigma square. And if I take the log of the above term, I would get, okay, so this is, you can think about this as the root 2 pi times sigma raised to the power negative n. So I can get negative n times log, right? This is the first term. And the second term, I just get rid of the exponential. This is what we have, the log likelihood. And now to find the maximizer for the log likelihood, the maximizer will be two-dimensional. A maximizer mu for mu, value of mu, and a maximizer for value of sigma squared. So we need to find both. And in this case, we will need some knowledge about multivariate calculus, right? This is a two-dimensional function. It's a two-dimensional function for mu and theta sigma squared. So how do we find the maximizers? So in this case, we're going to take a partial derivative against mu and a partial derivative against sigma squared. Okay, that's what we'll do. So let's try to set each first partial derivative to 0. Okay, so one key thing I want to say here is that we are regarding sigma square instead of sigma as the parameter, as the argument. So therefore, we are trying to express every term in terms of sigma square instead of sigma. Okay, to make that clearer, let me do this. So let me try to separate the first term. I will have negative n times log root 2 pi. Okay, now this one has nothing to do with either sigma square or mu. So it's a constant that will not affect our optimization. And then I should have negative n times log sigma, but I want to write it as log sigma squared. So that will give me a dividing 2 out there. So this should become, okay, so then I can make this a function of sigma squared. And this is because our argument is sigma squared. That's the key. And finally, for the last term, I don't need to do anything because it has sigma squared already. All right, when I express it this way, the first partial derivative I want to do is take partial derivatives. Okay, so the first one I will get is partial mu, okay? Okay, let's take a look at this. So firstly, let's do the against mu. Now you can see this term and this term has nothing to do with mu, so they can be gone, only the last term. And for the last term, if I do it, you see that it's only the numerator that's related to mu, right? So I'm going to keep the denominator and keep the sum. Inside the sum, I take differentiation against mu. So it will give me 2 times xi minus mu. And by the chain rule, I'm going to do differentiation of minus mu. So that will give me a negative 1. This is what I get from the chain rule. Okay, now you see this negative 1 and this negative sign will be canceled. And this 2 and the 2 in the denominator will be canceled, right? So what I'm left with is just that's it. Okay. And if I set this to 0, so set this to 0, set to 0. If I do this, this is what I want. Then what I can get from this, because the denominators doesn't matter, I can get the mu is just equal to what? Setting the numerator to 0. Then this numerator is, let me just express this term again, one more step to help you see it better. Sigma squared stays, I have the sum of xi, I from 1 to n, minus, because mu appears for n times in the sum, minus n times mu. Okay, so now I set this to 0. I will have mu equals to 1 over n sum of xi, which is our notation, x bar. Okay, so from the first partial derivative, by setting it to 0, I can find the maximizer of mu for the likelihood function. Do we have a question about what we did here? Okay, so now let's take the partial derivative for the second parameter, second argument, which is this partial sigma square. Okay, so I'm making it very clear that we treat sigma square as a whole thing. All right, so then the first term has nothing to do with sigma square. The second term, we keep the multiplier and log sigma square, derivative will become 1 over sigma square. Okay, because it's the whole thing, sigma square. And also here, I put a multiplier here on before this. Okay, so it's basically this thing multiplies 1 over sigma square, okay? And sigma square is the whole thing. So I would get minus 1 over sigma square square. This is what I will get from the partial derivative against sigma square. So it's just like the derivative of 1 over x is minus 1 over x squared. So I'm getting the same thing here. Okay, so you can see that we can simplify this a little, right? So basically, we are going to have negative 1 over, or maybe let me put it clearer so you can see it. Try to simplify this. Okay, let me just do this. So we try to set this, set to 0. Okay, set this equation, this expression to 0. Then what do we have? If you want to just solve this equation, negative sign can be gone. This 1 over 2, which is appearing in both terms, can be gone. So I'm just saying that this setting this to 0 is equivalent to say that we have n times our target 1 over sigma square. And I remove the negative sign in both terms. I remove dividing 2 in both terms. Plus this term, sum xi minus mu square, I from 1 to n, this stays. Okay, and I have a minus. I have a minus sign here. Times minus, and I have 1 over sigma square. Okay, I set this to 0. Okay, and now you see both terms involves 1 over sigma square. And we can remove it. We can cancel it. So this becomes 1. Okay, so I only have 1 copy of that. And then basically I can show that just 1 line of algebra. If I move this negative term to the right-hand side and I solve for sigma square, you can see that the sigma square would be equal to 1 over n. Okay, this will be the solution for setting the second partial, for setting the partial derivative against sigma square to 0. This is what we will get. But you see, this solution depends on mu, okay? And we have the mu solved in the first equation by setting to 0. So together, we are going to have mu as xn bar, set it to this way, and sigma square, which depends on mu, but we put a mu here into it, we will have summation. Okay, that's what we will have. Okay, and then finally, if we want to be rigorous, actually, we need to go to the second partial derivative, which means that we're going to take the log likelihood second partial derivative against mu, against sigma square, and also once against mu, once against sigma square. So that's what we call the Hessian matrix. Okay, so to verify, we need to verify that the Hessian matrix, let me just write it, it's defined as this. A 2 by 2 matrix, which is second partial derivative of the log likelihood against mu square, all right? And second partial derivative against this argument sigma square for twice. And here in the diagonal, off diagonal, we're going to have once against mu, once against sigma square, all right? And finally, once against sigma square, once against mu. So this is the Hessian matrix. We're going to verify that if we put the value mu and sigma square we obtain by setting the first partial derivatives to 0. These two values we obtain, if we put them here, then the Hessian matrix should be so it should be negative definite. So that's the linear algebra we need. So basically, the way to say that this is a matrix way of saying it's a negative number. So that's the thing we need to verify rigorously. We really want to say that this is the maximizer. But we are not going to do that for the sake of this class because we don't want to require too much for the linear algebra here. But this is the thing we should verify, okay? Verify it is negative definite at this mu sigma square equals the values we found here. Let me scroll this up a little bit. Xn bar and 1 over n summation xi minus xn bar square. Okay, at these two values, this matrix, this Hessian, is negative definite. That's what we need. So if we can confirm this, then with this confirmation, we will conclude that, yes, they are indeed the maximizers. So mu hat MLE is just Xn bar. Okay, and sigma square hat MLE is this formula. 1 over m summation xi minus xn bar square. I from 1 to n in the sum. Sorry, this is a little messy, but I'm just copying what's here. Okay, so one thing you may notice now is that the MLE estimator we found for the normal distribution variance parameter, this one, has n in the denominator instead of the n minus 1. Did you notice that? So this is the MLE we obtained, but it's not the unbiased estimator we are familiar with. We learned last time. So what I want to say is that this one here is that mu hat MLE is unbiased. Okay, this is what we know. But sigma square hat MLE is unfortunately biased. Okay, but this is what we have. So basically you see that there's no guarantee that the MLE estimators obtained by MLE are unbiased. Just as the question I think Brandon asked last time, is the MOM estimator unbiased? And the answer is also no. So for both MOM and MLE, there's no guarantee that they're unbiased. But one thing I can give you as a very nice theoretical property is that for MLE estimators, they are, in most cases, to be more rigorous, in most cases, they are what we call asymptotically unbiased. So by saying asymptotically, that adverb means that we are letting the m, which we mean by sample size, go to infinity. So if we have that happening, that we have a very, very large sample, then the bias can be ignored. The reason you can see here is that when the n is very large, then n minus 1 are n and n are almost the same, right? So in that case, the bias doesn't matter that much. So that's a nice thing about MLE. Okay, so we talk about two examples about finding MLE. One is the Possum case. We have only a single parameter. So we take the log likelihood differentiation, set the first derivative to 0, verify the second derivative is negative at that value. And this is a more complicated case because we have two parameters. So they need to be both estimated. So in this case, our likelihood function becomes a two-dimensional function. So the arguments are two-dimensional. The argument is two-dimensional, or we can say we have two one-dimensional arguments. And we have to take, when we take partial derivatives, then we have two partial derivatives. Both need to be set to 0. Basically, we have a set of equations to set to 0. And we solve the set of equations. And we have found those numbers, right? The values for that make the first partial derivatives to 0. And rigorously, we need to verify the Hessian matrix is negative definite. With that, we can claim that they are the MLEs. So the strategy is the same. Take the log likelihood differentiation. But once we have more than one parameter, it's a little complicated. Okay, so before we conclude, I'm going to show you a third example for which we don't take differentiation, but we still want to find the maximizer. So in the third example, we have x1 to xn as IID from a uniform distribution defined in this interval from 0 to theta. So theta is the upper bound of the interval, so it must be greater than 0. And the question is still to find the MLE estimator of theta. We call that theta hat MLE. So we still use the same strategy that here, the likelihood of theta should be defined, and uniform is a continuous distribution, should be the joint density of fx1 to xn given theta. Okay, for uniform, the density is actually known to be 1 over the interval length, right? So that's why the density can integrate to 1 on the interval. So therefore, for each xi, and you still do the factorization, IID, by x1, the density of x1 to the density of xn, given theta. Okay, and we know that each one is 1 over theta, right? But the thing is that, just try to be clear about this. This is the key thing here. So what is the xi? For xi, what's the density? For uniform, we actually know that the density is, like I said, 1 over theta if xi is in this interval from 0 to theta, okay? But outside of this interval, it is 0. Otherwise. So the density has the sharp change, all right, at the two boundaries. So we need to take that into account. So in other words, we need to say that, so basically, and because theta itself is the range, is actually the upper bound. So therefore, when we write it, we need to incorporate this. So we cannot drop this part because it involves theta. So what we can write it to uniform it is that we can write that the density is 1 over theta times the indicator that xi, the random variable value, is, maybe I put it here, close interval, less or equal than theta. So this indicator function is a way for us to include the boundary into account. So when xi is less or equal than theta, we will have indicator function taking value 1. Okay, so its value is 1 if this set is satisfied. Otherwise, we will get a value 0 from the indicator function, and that matches what we have here for the density. So I want to emphasize again here, we include the indicator function because theta is the boundary of our definition here. If we ignore that, then we lose information that theta provides about the density. Okay, so with this, then we can have the L theta will be equal to, for each term, so it will be 1 over theta times the indicator function that x1 is less or equal than theta, multiply up to 1 over n times the indicator that xn is less or equal than theta. Do we have question about this expression? So we're still multiplying the densities together, but for each density, the theta defines the boundary, so we need to incorporate that into the indicator function. Otherwise, we lose information. So together, you see, combining them, I can put 1 over theta to the power n, combining these terms. And how do I combine the indicator functions? So let me ask you, so under what case will all the indicator function be non-zero? Right, so you see, this is a product of indicator functions. If one indicator function is 0, then the product will be 0. So the only case that this is non-zero would be that all the indicator functions are equal to 1, right? And when all the indicator functions are equal to 1, it means that from x1 to xn, they are all under theta, right? And that translates to the maximum of x1 to xn are under theta, right? So this is the key step. So from here to here, to make this non-zero, we need all the x1 and xn to xn under theta. So I put it here. I change the indicator function to disjoint indicator function. So when they all hold, the indicator is 1. Otherwise, it's 0. Okay, and I can re-express this joint indicator function by the maximum. So that means the maximum, now I say I goes from 1 to m of xi. So this expression means that I'm taking the maximum of x1 to xn. I need this to be under theta. It's the same way as expressing the joint event. x1 is under theta, x2 is under theta, and xn is under theta. Okay, now you see we are going to find the maximizer of this likelihood function. And in this case, taking the log or taking differentiation will not work. The reason is that here, this is not the indicator function is not really a differentiable function for theta. Because if you think about it, let's see that we fix this maximum, okay, and we change theta. Then we can see that if theta is less than the maximum, the indicator is 0. Once the theta reaches the maximum or becomes larger than the maximum, indicator suddenly becomes 1. So this is a jump step function. It's not differentiable against theta. This is the key. Now, not differentiable with respect to theta. So because it's a step function of theta. So in this case, we have to think about another strategy, right? Just by the definition of maximizing the function of theta. So we can imagine that here the function is this. Let's say theta is this, L theta is the y-axis. So let's say that we find the maximum of our xi. Say it's this. It's right here at this value. Then by this definition of L theta, if theta is on the left of it, we are going to have 0 from the indicator function. So the function will stay at 0. The function will stay at 0. And there's a circle here, means that once it reaches this value, it will suddenly jump to 1 for the indicator function. But it becomes 1 multiplied by this. And that will be, actually, I'll just mark as 1 over theta to the power n. It will suddenly reach the value and stay at this value afterwards. So this is how the maximum, how the likelihood function it will not stay at this value. It just, I made it bad. Sorry. I would say it become, forget about this. I thought it's a wrong example. It's a wrong illustration. So theta is this, and let's say max xi, I from 1 to n is here, okay? So before this point, it stayed at 0, that's correct. After this point, it will become 1 over theta to the power n as theta changes. So theta reaching beyond this point, you will get here. So here it will be equal to, I'll just say, it's 1 over the max xi to the power n, because that's the value of theta. And then after that, it will change in the trend of 1 over theta n, all right? And so depending on like the shape of the theta, so it should be x to the power, theta to the power negative n. So we know that shape will actually decrease as theta increases. So it become like this, okay? So if we draw the curve like this, you can see, oh, before this point, the likelihood is 0. After this point, likelihood is non-zero, but it decreases as theta increases. Okay, so from this, then you can immediately see the maximizer of this likelihood of theta should be this point, should be this value, should be just the maximum of xi. So to help you understand this better, it means that we take the maximum of the set x1 to xn. That's what we need. Okay, sorry, I think we're running out of time for this example, but we'll come back to this on next Wednesday, and you can think about this. This is a more challenging case because the likelihood function is not differentiable everywhere. So that's why we cannot just take that simple log transformation and differentiation strategy. That we are using exactly the definition of MLE. Try to find the maximizer of the likelihood function and try to interpret this figure after your midterm. Okay, so try to see why I draw the figure like this. Okay, so then I'll see you on next Monday for the midterm, and I will make an announcement based on what I said about the midterm format, so people who don't come to the class can still be informed. All right, so I'll see you next Monday. Bye.